All right. Good afternoon, everyone. Welcome. My name is Sebastian. I'm a member of the Recreate communication team. For those who are new, Recreate is a Horizon Europe initiative, which is focusing on developing actually circular solutions for the reuse, remanufacturing, recycling of, especially of carbon and glass fiber reinforced composite materials. Thank you for joining us for the fourth webinar of this series. This is a part of the Challenge Circularity Initiative, trying to promote solutions that will help us transition into a more circular economy. Today's webinar is titled Building Better Next-Gen Composites, and we'll be especially focusing on the wind power energy. I'm very happy to introduce the three speakers that will be presenting today. Giulia Altamura of Politecnico di Milano will open the session by presenting novel smart resins enabling the circularity of composites. Then it will be Frank Richard of REST, who will introduce a new rotor blade design for wind turbines. Following him will be Dominic Voigt of Invent, who will present the design guidelines for adhesive bond lines of such wind power rotor blades. Each presentation will be followed by a Q&A session, so you're more than welcome to write your questions into the chat or raise your hand and ask them yourself. And now, to stick to the timing, I would thank you again for joining us, and I'll give my word to Giulia from Politecnico to start with her presentation.
Good morning, everyone. I'll try to share my screen. Okay. Can you see the presentation?
Yes.
Not in presentation mode. Yeah, there you go. Yes.
Yeah, perfect.
Okay, thank you. Okay, good afternoon. I am Giulia Altamura, and I am a PhD student at Politecnico di Milano, and my research focuses on smart resin for the circular economy. So, fiber-reinforced composites are mainly made by an epoxy or an unsaturated polyester matrix, typically reinforced with glass or carbon fibers. The final product typically features great thermomechanical and chemical properties that are also tunable by modulating the fiber-resin ratio. However, we also have some issues typically related to the recyclability, which is often difficult and non-cost-effective, leading to landfilling and incineration being the preferred end-of-life choices. Moreover, toxic chemicals such as bisphenol A, epichlorohydrin, styrene are often used for matrix formulation, making this formulation not really safe. So our question is there a way in which we can solve this? The answer to us is pretty straightforward, and it's called bitumers, which can be considered a sort of bridge between the two most traditional classes of polymers, thermoplastics and thermosets. Why? Because they have the reprocessability and recyclability of the former, but the solidity, the network of the latter. In particular, they are made by a thermoset-like cross-link network, which, however, can become dynamic upon the application of a specific stimulus, such as temperature. It's the most common one. These dynamic exchange reactions are often enhanced by the presence of a chemical, so a catalyst. This molecular arrangement, in this way, enables reprocessability and recyclability in an easy way. So, coming back to our pros and cons, how can bitumers help in this sense? They can help by making recycling easy and cheap, or at least cheaper. Reprocessing and reusing in this way become the preferred end-of-life choices, and they can be formulated by using non-harmful and sometimes also bio-based chemicals. So here in Politecnico, we are developing some new vitrameric matrices for glass and carbon fiber reinforced composites. Until now, I have developed 3 different systems, 2 epoxy anhydride bitumers and 1 unsaturated polyester bitumer. Common to all these 3 systems is their internal chemistry of exchange, meaning that they are all based on transesterification reactions that occurs between an hydroxyl and an ester group. But how can we say that a bitumer is a bitumer and not just a thermoset? This can be said by just a simple experiment called stress relaxation, in which a constant deformation is applied to the material, and we just monitor how the stress and so the modulus changes over time. If it's a V-trimer, thanks to the dynamic exchange reaction, we expect the modulus to decrease. So we can say that if it relaxes stresses, it's a V-trimer. Otherwise, it's a thermoset. So coming back to our formulations, I'd like to start by introducing to you the epoxy anhydride V-trimers. They are pretty similar in terms of formulation, meaning that they are all based on the same epoxy oligomer, PHT, which is obtained from brown microalgae, so it's also bio-based, partially. As for the first formulation, this is pretty simple. It's a two-component formulation that also employs glutaric anhydride as hardener. In the second case, we have used a mixture of anhydrides and a transesterification catalyst to help the exchanges between hydroxyl and esters. This catalyst is called TBD. So looking at the characterization of these two materials, we can say that they are completely cross-linked, so their properties show epoxy-like features. But of course, we have some differences, in particular with the glutaric-only formulation. Glutaric anhydride provides a great flexibility of the molecules, which allows us to work without the aid of a catalyst, since the molecules can interact with each other pretty well by themselves. But flexibility in polymer chemistry also means a lower TG. So our TG is around 80-90 degrees, meaning that it's typically more suitable for less performing composites, such as glass fiber reinforced ones. On the other side, the mixture of anhydrides give us a lower flexibility that gives us, in turn, higher TG, but we need a catalyst, TBD indeed. Now that we have characterized our resin, we want to know if it's a V-trimer or not. So, as I said before, we need to do some stress relaxation experiment. As I mentioned before, if it relaxes, it's a V-trimer. So if the modulus decreases over time, and they do, it's a V-trimer. So we can say that these formulations are both V-trimers. And we can also observe that relaxation is faster as we increase the temperature, of course, due to kinetic reasons. In the first case, stress relaxation actually it's pretty fast. We can relax fully our resin in 15 minutes at 200 degrees. But we could also push this relaxation further by increasing the temperature, since the only limit we have is the material degradation that typically starts occurring around 250, 270 degrees. Since these are our properties and they are more suitable for a glass fiber reinforced composite, we decided to produce with this material GFRC and to reprocess it. On the other side, instead, we can see that relaxation is a bit slower. At 200 degrees, we get full relaxation in only 2 hours and a half. However, I let you notice that the curve at 200 degrees is a bit different in shape with respect to the others, and this could be a hint of something occurring inside the material, possibly, maybe, catalyst deactivation. Since TBD is pretty sensitive to high temperatures. Therefore, we decided to create a carbon fiber reinforced composite with this material to reprocess it by recycling it, but staying below this temperature. Going to the end-of-life management, for the first composite, we decided to reprocess it in 2 different ways. Shape reconfiguration, which means imposing a new permanent shape to our composite by applying a thermomechanical cycle to it, basically a thermosis, in which we repeatedly heat the material at the relaxation temperature for the relaxation time to enable the rearrangement of the macromolecules in the new deformed shape. In the second case, we decided to self-weld 2 different plates of composite together. Again, we heating them up at the relaxation temperature for a time long enough to enable relaxation, and we ended up with this joint with a pretty high adhesive strength of 54 megapascals. As for the recycling part, we took our composite and dissolved it in butanediol, which is a diol containing OH groups, and in which TBD, so the transesterification catalyst, was also dissolved. And the complete dissolution of the matrix was obtained in 30 minutes at 180 degrees Celsius. So we were able to recover the organic fraction and the reclaimed glass fibers that were both possibly reusable for second generation materials. I mean, you notice that in this case, we have created a sort of extrinsic Vitimer because the resin itself, so also the matrix, was vitrumeric, but we were also able to create exchanges between the resin and the solvent, thanks to the TBD dissolved in it, meaning that this way the resin was able to dissolve itself. Now, coming to the last material, unsaturated polyester. Let's say that in general, the main problem at commercial level of unsaturated polyesters is that they are usually cross-linked with styrene, which is very good at cross-linking, of course, but it's not the safest chemical on the market. Therefore, our purpose was to introduce a replacement to it that was both not hazardous, but that was also able to induce transesterification reactions within the network, creating a Vitimer. Therefore, we started by using a vinyl ester monomer as a base that contained esters, but not hydroxyl groups. And we added, instead of styrene, hydroxyethyl methacrylate, HEMA, which not only was able to cross-link the Vitimer, but also introduce some hydroxyls. Together with it, we also added a transesterification catalyst to help with the exchanges. So as we can see, also in this case, we have a Vitimer because stress relaxation could go down. And we also see that the higher the catalyst content, the faster the relaxation. In this case, actually, relaxation was not really, really fast, but was acceptable. With this matrix, we produce a glass fiber reinforced composite that, also in this case, was reprocessed with shape reconfiguration, as in the case before. Also in this case, I can have you have a look at the thermomechanical cycle that we applied to our materials. So basically, we heat the material up above its TG to deform it, and then we heat it up at the relaxation time in the constrained configuration. So we keep it constrained, we allow the material to relax, then we cool it down, and then we repeat this process, this time without constraint, so that in the last step we have an elastic recovery. And we can end up in the final step, so in the red dot, in the red step, with a material that is plastically deformed. So we have no longer temporary elastic deformation in it. So to conclude, why Vitimers are a good alternative for matrices of composite? Because they can be biodegradable, non-toxic. They enable the reprocessing of the material and extend in this way their service life, but they can also be recycled, enabling also the recovery and reuse of the recyclate. And all of this is compliant with the circular economy principle. So we can say that overall we are pretty satisfied with our results. Thank you for your attention. If you have any question, of course, I'm here.
Thank you, Julia. Yeah, please, if anyone wants to ask a question, welcome to raise your hand.
Well, Nick Beanie, nice to meet you, the Rangos Consulting. I have a question. Thank you very much, Julia. Actually, I have two questions. Thank you, Julia, for the presentation. First, how does the recycling process of Vitrimer differs from the recycling process for epoxy, for example? Because I've seen you use a solvolysis, which can be used for epoxy as well. First question. Second question, exactly there. Second question, do you think that 2 hours or even 4 hours for the unsaturated polyester is something relevant for the industry, 2 hours reshaping?
Okay.
Thank you much.
Thank you for your questions. So starting from the recycling part, yes, it's similar in the mechanism, of course, but here we are exploiting the ability of the material to exchange. So when we do conventional solvolysis, we are breaking bonds, basically, because we are using a catalyst that is able to break them. While in this case, the material is transesterificating. So you are creating new oligomers that are possibly also different from the one that are produced by conventional solvolysis, and so could also be reused in a different way. I think I hope this satisfies your question.
Okay. Yeah, thank you.
Okay. And as for the time, so here we selected 4 hours, even though relaxation occurred in 2.5 hours. Let's say that we decided to stay safe. These times can be optimized by also taking in mind that relaxation tests are carried out in a rheometer that, of course, has an optimized heating system, while, of course, our oven doesn't have this kind of efficiency. But 4 hours can for sure be reduced. That's for sure.
Okay, thank you very much.
Thank you.
Okay. Yeah, Amin, you have a question? I can see your hand. Please go ahead.
Yeah, just I want just some examples of application of such technique and such method of recycling. So once you heat and you wait until cooling, so what is the application of such a product after such a process of recycle? Just give me an example, if she can, you know.
Yeah, sure. But well, for example, if you have a blade or something that has been deformed by time, by creep, you can just heat it up and you can recover its initial shape. So you don't have to
and do you think
throw everything away.
What about the stiffness and the elasticity and the shock absorption after heating and cooling such reaction or such a product? So it is going to change in any parameter?
Yeah, actually, stiffness, we have seen that by doing multiple stress relaxation, typically we have a higher TG, higher modulus, because we are introducing some irreversibility inside the system, because a side reaction occurs, and for example, instead of creating ester and hydroxyl, some ethers form, and ether are irreversible. So typically we get improvement in the TG because it gets higher. So we have a bigger glassy plateau, and yeah, better performance in that term. I don't have any data about shock resistance, but in general, when we do this thermal treatment, we heat it up slowly and we cool it down slowly. So for the thermal point of view, that shouldn't be a problem.
All right. Thank you very much.
Thank you.
Thank you for this discussion. Frank, I think you can take over.
Okay, great. So hello everybody and welcome. My name is, as introduced, Frank Richards. So, and I'm a CEO from REST, which is a company worked mainly by measure and analyze on-site energy demands and local renewable potential, turn those data into a solid energy concept and support implementation. So what we do is from planning through permitting and realization. We also provide micro, mini, and small wind turbines in the range of 2 to 250 kilowatt, including our own developments. And we combine wind with solar and storage to help customers achieve a high level of energy autonomy. Today, I'd like to share some work from the EU project Recreate. So focus on a circular rotor blade design, which is a segmental blade concept designed for recyclability and maintainability. This short session is about a simple idea. Wind energy is, of course, sustainable, but blades remain a circularity bottleneck. So in Recreate, we look at what must change so that composite materials like rotor blades can be reused, repaired, or resampled and routed into higher value end-of-life pathways instead of becoming waste. Let's start with a scale. Multiple studies project a steep increase of end-of-life blades over the coming decades. Commonly cited global forecast indicates around 43 million tons of cumulative blade waste by 2050. So we know that is something we need to do. At the same time, policy and industry pressure is rising in Europe. Landfilling of composite blades is increasingly restricted. So Wind Europe has publicly called for a European-wide landfill ban. So in Germany, we have already this kind of ban. So I think several countries will come up and have bans in place as well. So the situation is quite clear. I mean, volumes goes up and the easy disposal route goes away. That's why we need solutions that work not only technically but also economically at scale. This slide summarizes today's solution landscape. Landfill is, of course, the simplest historically, but it's increasingly banned, as I said, or socially unacceptable, and it offers no material recovery. So that's the main part. We just put it away, but we can't use it for anything else. Incineration can recover energy, but you typically lose the fiber value and face emissions concerns. If it goes to cement co-processing, which is of course widely available and can be cost competitive, but often results in downcycling. So it means we have only limited control over fiber value. The mechanical recycling has relatively low energy demand, but the output quality is often limited, useful for some application, but not as a true closed loop. Pre-releases and sub-releases, as we also see from other partners within our project, can recover higher value fibers. That's nice, but especially for carbon fiber composites, that's great. But scaling and cost and process complexity remains key barriers. The big takeaway is end-of-life technology alone is not enough, and the product was never designed to come apart cleanly. Recycling stays expensive and contaminated, or we have just a very low value. So here are some design principles that matter if we want really true circularity. So we have on the modular design, so parts can be separated and handled. Then we talk about a mono-material mindset, wherever possible, so streams stay clean. Reversible joints, mechanical solutions or adhesive systems can be released intentionally. So that's one of big intentions here. Then we have these standardized components enabling repeatable manufacturing and future reuse. So that's good. And of course, a material passport, so we really know what's inside and how to route it. And finally, a circular material flow. So it means where design choices are made with end-of-life routing in a good way. This principle leads directly to our approach. So on the left side, you see we have normally these kind of in monolithic blades. So it means a lot of people working on something, then we glue the complete roadbed together, and then we have a monolithic blade. That's how we handle that. And our intention is that we propose at least that we build such blades from segments and interfaces that are intentionally separable. So really, we can take those blades apart after using it. These monolithic blades makes a very we can efficiently manufacture those, but there's really no way that we can disassemble those later. The K concept within our segmental rotor blade architecture is that we don't treat the blade as one inseparable object. Instead, we treat it as a system of function modules. So we try to rearrange a load path from wind through the structure of the blade to the hub. These function modules, we should like to manufacture those with the best suited processes and connect this through. And that is what is quite interesting here with defined interfaces designed for both load transfer and, of course, end-of-life separation. So in the task 4.3, we have this kind of modular idea. As you can see here, we have different segments which are made from different materials and put those stuff then together by gluing those parts together. In Recreate, the work package I lead, we just build up a small demonstrator so that we can validate the concept. So the system is, you will see it on the next picture. So we can here have the different elements of how they look like. So we have a spar, which is red here on the picture. It could be made from glass fiber or carbon fibers. We would like to use for those structural array recycled material, and because we want to protrude those spars, and with those protrusion we get very high quality, and that means if we have weaker material by the process, we can really lead to high quality, high load transferring spars. Then we have ribs. Those are made from end of life material, so we cut them really off from old rotor blades, or maybe some sandwich structures, or by water cutting. And then we have this leading edge part, where we try to introduce thermoplastics, which is preformed. Thermoplastics, since these leading edges are normally eroded during the operation, so everybody needs a long-lasting work to repair those leading edges on place. So with our idea that we can really dismantle those leading edge from the structure and replace it by another one, it's great. And then we have the thermoplastics, which we can guide to a nice recycling part. These trading option alloy parts on the back are produced out of glass fiber or sandwich plates. And the most point is, of course, that those parts will bond together by using debonding on demand methods. In our work package, we will also demonstrate by controlled heating, using either that we put the complete structure in the oven or by induction heating to a temperature, to an activation temperature of a heated system, so that we can really dismantle those parts after putting on the heating. So what does this structure achieve, or what we want to achieve here is that we find clear load paths and interfaces, so we can integrate end-of-life composite material where it makes sense, like ribs cut from old blades, or while keeping performance under control. Second, the concept shifts major parts towards machine support processes. As you see on the slides before, most likely the rotor blades are handmade, so a lot of people put a lot of material inside the mold, and so that is not a really controlled process. With introducing these kind of protrusion or thermoforming, we could largely reduce the people we need for producing those blades. Also, maybe it's a way how to get blade manufacture back to Europe, because right now mostly all blades of wind turbines, which are set up here in Europe, are made and manufactured in China. So these kind of machine support processes will supporting repeatability and quality. And third, once parts can be separated cleanly, material purity will be improved, which directly improves recycling option and value, of course. And fourth, the modular approaches enable this replacement instead of scrapping, especially for the leading edge, which is, as I mentioned, erosion prone in real operation. So we tested already this kind of leading edge exchange procedure in our work package, and shows that it's at least possible that we can do so. A very honest learning from the demonstrator work is also that the main bottleneck today is assembly, because as you can see, we need, of course, we have multi-part alignment, and fixtures are still labor intensive. So we need to work thermoplastic leading edge. We have then this glass fiber shell parts manufactured on an external mode. The ribs you can see here are really produced from old rotor blades, so cut off from rotor blades. Then we have this protruded glass fiber. It was just first phase was a glass fiber, but now we also did it with a carbon fiber. And what is quite important here, you see those black parts, these 3D printed carbon fiber cleats and all the auxiliary web. And so we really, those cleats are very important because these are, we connect different parts through those cleats. And we check out whether the loads are transferred through those cleats in a wide way. And only the surfaces of these cleats we use these adhesive bonding with the bonding on demand solutions, which supports these that we really say, okay, we can control the disassembly process later on. The validation is not only conceptual, so we report static and cyclic structural testing. So we want to see whether those load passes are really working. We will also not have just the static loads on it, but also try to have some dynamic loads. So what we do right now, also next weeks, we will start to have some 1 million cycles, load cycles on it, to see whether the structure will really hold. Okay, that's more or less what we want to show. The core message is quite clear. So we need a design which really allows for better recycling, and on that we need to see whether we can use those interlock materials also quite efficiently. So big wins of this fast segmental debondable architecture will be cleaner separation and better end-of-life routing, and of course maintainability by replacement, like this leading edge exchange, which can extend service life and reduce waste. Okay, that's from my side. Thank you for your attention, and of course I'm happy to take some questions from you.
Thank you, Frank. Any questions? Armin, please.
Everything's clear. So
yes, thank you for this lecture. It's a great lecture, actually. I have very big interest in recycle, especially in fiber and plastic products. So now the main issues with the blades is the core material. Core material is, and what they are using is a wood balsa. Now, creating or inventing a new let's say core material which can use the shredded fiber or shredded old core material mixed with the polyurethane and creating a high density polyurethane, which will help a lot to be reused as a core material many and more, so many times as much as you wish. What do you think about this idea?
Of course, I mean, our intention here was to avoid to use maybe these combined assemblage structures, because, as you said, they are not very easy to recycle. And that is due to our design. By introducing those ribs, because normally you have the effect that you have this kind of shaking the surface within the rotor blade load cases. And by introducing those ribs, which is not a new idea, I mean, the first airplanes has been built by this concept, we can avoid that we have these buckling of this area, of the big surfaces, because we have some ribs underneath. Right. So the intention was really to use more clear, pure material. So in that sense, right, we have really those kind of glass fiber reinforced areas as pure material, which is much easier, right, to recycle it. The sandwich structures, we would like to use those for end of life, for the cutting off for the ribs, because this is something we can say,
Right.
okay, is scrap material afterwards, but for this, we need to guide the new load pace through the blade. That's why we introduce these massive spar made out of carbon fiber. So that's the intention. So avoid mixed material, because that is, of course, the problem by recycling.
Right. Thank you very much. I would like to contact you after this lecture. I have something which I can tell you that we had a lot of need for material, and we have a lot of fiberglass waste and carbon fiber and plastic and polycarbonate, acrylic, and we created a chemical reaction from this waste to make high density polyurethane foam with extremely good, affordability, extremely strong. I would like very much to contact you after this, just to discuss about this issue. I have a lot of examples, a lot of that's.
But keep in mind that right now, what we show is here. We would like to demonstrate the concept and principle works. We right now talk about very small blade. So we have these kind of 6-7 kilowatt turbine with a 7-meter long blade. So actually, we don't need a lot of material to produce a blade now.
Right.
We want to show that there are design principles which could avoid the problems of. We talk about 300 gigawatt of wind coming up in Europe, mainly offshore. We need to have something in mind to avoid that all those blades from those turbines will come up with a big mess. As we can't landfill it, that's for sure. So we need other possibilities, and our intention here is that we say, okay, we need a different design, which allows us to separate the parts after a lifetime.
I understand. Yeah. Great. Anyway, we'll keep in touch. Thank you very much for your information. Thank you.
Thank you, guys. I think we have another question.
Yeah. Okay. I like this modular design, debondable, but then also, there are, if you split things up in sections, there are also loads to be transferred, and especially when you look at the spar, and you have multiple sections, there are quite high loads to be transferred. How do you see that happening?
Yeah, that is. What we just don't have this small segment. We do a lot of FEM simulations in order to see how the loads are guided from the air pressure through the structure to the hub. That's the main idea. Besides of generating power, we need to organize it. And actually, the FE simulations shows quite good results. So. Our intention was, of course, you have seen this protrusion of the spar. So the main problem is, of course, that if you have an aerodynamically well-shaped rotor blade, we can't use the protrusion of the spar above the complete length of the blade, because we need to change the shape. That's why we have this kind of intersection. Of course, there's still some question marks behind our concept. So, but the general idea that we can organize the load paths in a different way, and then we have functional modules which can say, okay, the ribs will guide with the cleats and the ribs, we guide the pressure from the outer surface through the bar, and that works in the simulation quite well. So we see that we really can organize the load paths in that way that we can really use these kind of end-of-life material, which is quite weak, of course. But introducing, let's say, the right design with the right number and the right thickness of those ribs really can guide the loads from the outer surface to the spar. And the spar, of course, if we have this protrusion of the carbon fiber, we get extremely high quality of those spars. I was working right now like 30 years in the wind business, and I always see that by using the methods we have right now, we have very high safety factors, because we can't guarantee in the production process that we have really the same behavior. So that's why we have safety factors up to 2. And by introducing those more mechanical industrial ways, we can reduce largely the safety factors. So using those potential to effectively use those materials in our new design. That's the intention.
Looks quite interesting. Yeah.
Okay, thanks.
Yeah.
Okay, the debate sparkled another question. Please go ahead, Didier.
Yes, just a small question. Thank you for this very interesting topic. Just a question, is it harder or how is it to balance the blade in comparison with the standard processing which is under production today?
So we start with a design that we use a common blade. So we have an actual design, and if we try to, because we talk about stiffness, strength, bending curve, frequency. All those things need to be in mind in order to keep the dynamic behavior of the overall turbine. So if you want to exchange, let's say, a common blade, we really need a design which mainly also fits in these borders of frequency, bending curve, and so on. And that's what we have achieved. So the design right now was that we have more or less the same weight of the blade and the same eigenfrequency. The first and second and third eigenfrequency was, let's say, some 5-10% different. But if we kept the same, let's say, behavior of the blade itself, that was quite important for us, that we don't change the complete dynamic behavior of the turbine if you exchange, for example, the eigenfrequency of the blades. So by the design, we have a lot of design parameters. As I said, the ribs, the number of ribs, thickness of the ribs, and so on. We have a lot of nice design parameters where we can try to find an optimized solution of all those parameters in order to stay within the borders of the original blade.
Okay, thanks.
Okay. Thank you for contributing to the discussion, everyone. Next up will be Dominic. He'll actually explain a little bit more about the debonding on-demand solution that is a part of this concept as well. Dominic, you're more than welcome to share your screen.
Yes, of course. Thanks for having me. So, just a second. It is this one. So, can you see something?
It's loading. Yeah, we can see it. Yeah.
Okay. Top. So, yeah. Hello from my side. Like Sebastian already said, I would like to introduce you to the presentation of the results of my master thesis about the development of design guidelines for adhesive bond lines in segmented wind turbine rotor plates. For the work package 4 of the Recreate project, and maybe it's a good addition to the presentation of Frank before. And before I start, maybe a short intro to myself. My name is Dominic. Some of you already met me at the meetings in Nantes in, I think, 2024. At this time, I wrote my master thesis about this topic under the direction of Mark and Fabian. And meanwhile, I work at Invent in the same group like Mark Opitz and do a lot of structural analysis in combination with system engineering or project management. So let's start with, in the beginning, I would like to explain the motivation behind my work. Here on the left side, you can see the design of a conventional wind turbine rotor plate in which the adhesive bonding plays a major role in structural integrity. So it always comes to a very high consumption of adhesive, typically around 6 weight percentage of the whole rotor plate. And additionally, the conventional blade design here on the left side often involve blind bonding, for example, in the area where the upper side meets the lower one. So in this part here. The term of blind bonding means that the quality of the bond line cannot be fully controlled during assembly, which can compromise the structural integrity and increase the risk of some defects in the bond line. From a sustainability perspective, conventional blades are also difficult to recycle, and the reusability of individual components is strongly limited. And these 3 points are where segmentation offers a promising alternative to the conventional rotor blade, which allows us that damaged components, like Frank already said, the trailing edge of the wind rotor blade can be replaced more easily, which extends the service life of the blade. And at the same time, it enables reuse of intact components in new product life cycles, like new rotor blades in the same design. Another point is that the segmented rotor blade design enables more controlled adhesive application, which supports quality assurance and reduces the amount of bonding effects. So in this combination of these 3 points, the promises led to our Recreate motivation to develop a segmented rotor blade by using adhesive bond lines. So now moving on to my approach. With the previous presented Recreate motivation, my aim was to develop adhesive joints with the highest possible load capacity and at the same time a reduction of adhesive consumption and prevention of blind bonding. So in the beginning of work package 4, we discussed different segmentation and joint concepts, including the use of end-of-life material, like Frank already said, for the ribs. The idea behind this step was to identify locations that are structurally critical and to define for these ones suitable joining strategies for the segmented design. So based on this, I picked one certain connection, and this was the adhesive joint between the outer skin here on the right side and the rib structures, which I transferred into 2 main design approaches, concept 1 on the left side and concept 2 on the right side. By this, concept 1 is based on a more conventional joint design where the load transfer is mainly achieved through the adhesive bond line by adhesive fillet. And concept 2, in contrast, introduces a cleat joining or a cleat-based joining approach, where the load transfer is more controlled and guided through the cleat geometry, while the adhesive layer is used to connect the components and enable efficient load introduction into the spar later. For both concepts, I investigated, both concepts were then investigated numerically to evaluate their structural performance before moving into physical testing. Therefore, I used different modeling methods. For concept 1, I modeled the adhesive fillet by using volume elements. And in concept 2, I modeled the adhesive layers by using cohesive zone elements. After building the models, I did some parameter studies where for both concepts. These studies helped me a lot to understand how design parameters influence my load capacity, adhesive usage, or at the end, the overall joint behavior. For example, I studied parameters like geometry parameters of the adhesive fillet, material parameters like different adhesives, for example, epoxy adhesive or polyurethane. And for both concepts, I also studied the influence of the percentage of TEPs, which are particles which expand by heat and therefore destroy the adhesive layer to debond my adherents. Yeah, and finally, the numerical results were then validated via experiments in form of subcomponents. Instead of testing a whole blade or a whole section, I manufactured T-joints by myself and tested them on a Swig testing machine under an equivalent load case. And with this validation, it's allowed me a controlled comparison of performance, failure behavior, and reproducibility between the two joint concepts, which is shown on the next slide. Overall, I can say that concept 2 showed a significantly higher load capacity. The load capacity increased by 21% compared to concept 1, while maintaining a comparable or while maintaining same amount of weight or the same joint weight per specimen. In terms of adhesive consumption, concept 2 also performed better. The reduced adhesive usage lowers the amount of defects, which is especially important in large-scale manufacturing of such components. And in numbers, the reduction of the adhesive was about 95.7% in my numerical studies, which were then corrected by my experience to about 70.5%. Yeah. Additionally, concept 2 showed improved reproducibility during assembly. This was reflected by lower standard deviation in my experimental tests, which indicates a more stable manufacturing quality of concept 2 in comparison to concept 1. Another point was that concept 2 offers a higher reusability potential, contributing to increased sustainability. This is mainly due to the possibility of reusing cleats after disassembly, after the debonding on demand technology for maybe other rotor blades or other parts. So based on this comparison, I selected concept 2 in the segmented or for the segmented recreate rotor blade. And for this selection, there are a fire alarm. So
I hope you're not in danger.
Maybe I have to stop and go out. Oh no, it's over. Okay. Maybe I ask someone if everything is okay.
Check, yeah, please.
So this is a short pause for me.
Just be safe, please.
So we have hot presentations here. That's why we up the fire.
I think it was a test or something.
Okay.
Yeah. Okay. So where did I stop? And so I selected concept 2 for the recreate rotor blade, and I tried to derive design guidelines for the future application. First of all, I recommended that the use of fiber reinforced plastic cleats, because they show a higher mass specific load capacity than aluminum, This means they offer improved performance by lightweight structural design and allow a more load optimized geometry by layering the UD layers of a composite material. Second, I recommended polyurethane adhesives, where because of their high fracture energies in both peel and shear directions, which delay failure under bending loads. And at the same time, there are lower strength ensures that the failure always occurs within the adhesive layer rather than damaging my adherent. And this is a key advantage of the design because it always enables reuse of the structural components after debonding on demand separation. The next one is that I defined the use of different debonding on demand technologies on two different adhesive joints. For example, one technology at the adhesive surface 1, which was the connection to the end of life rib, and another one at the adhesive surface 2, the connection to the outer skin. Possible technologies for the recreate rotor blade were then the addition of TEPs, like I said before, and the application of inductive detachable adhesives. Another major part of my conclusion was the implementation of the implementation of a design extension. Here you can see it on the right side, by an extension with omega ribs. So, like I said, the cleats are structural joining elements that enable the segmentation while maintaining high load capacity. So this design enables a load application position for releasing the cleat from the adherent, which supports disassembly after activation of the debonding on demand adhesive. And second, in numerical studies, I showed that it increases the stiffness significantly. My results showed either an increase in stiffness by 22.6% or a reduction in weight by 15.2%, depending on the design target. So, and on this point, I already finished my master thesis and left the project at work. But a lot of my findings were implemented within the real demonstrator, especially the design of the cleat structures, which were simplified, manufactured by using fiber reinforced 3D printing. You can see them here in the right corner in black color. For the adhesive bonding, there were different systems were used depending on the location. And right now, after manufacturing this section of the segmented recreate rotor blade, the design feedback was very positive. The functionality of the cleat structure was fully validated, but further optimization is still required for the real load cases. In work with Frank, we already discussed that the bond area of the cleats needs to be increased to meet the higher structural demand in the full scale application. Yes. If there are any questions, feel free to ask them. Otherwise, thank you for your attention.
All right. Thank you, Dominic. Any questions? Amen, please. You are muted if you are speaking.
All right. Oh, yeah. I mean, the question is, have you tried this concept of connection for the blades, or still is under experimental study?
Yeah, like I showed in the last slide, we already implemented the cleat design into our Recreate demonstrator, which was shown by Frank in the previous presentation. And like design back positive, but there are a potential of optimization.
Right. Okay. Great. Thank you.
All right. If there are no more questions, I would like to thank everyone for joining today, and of course all the speakers for providing the very valuable information. The recording of this webinar will be available on our website, so you'll be able to review it, and there's also much more information on our website at recreatecomposite.eu. I would also like to use this opportunity to invite you to a conference that we are organizing in April. It's going to be the final conference of the Recreate project, taking place in Brussels, but also online. It's going to be a hybrid event, and there's going to be many such technologies presented there. So you are more than welcome to reserve your spot right now, because the seats are limited, both for in-person and online participation. And really looking forward to seeing you there. Thank you again, and goodbye.
Thank you. Bye.
Bye-bye.
Thank you. Bye.
Bye.
Bye.